Hello everyone, this side Nisha, roll number 2127, and my topic is Lebesgue bounded convergence theorem. Before we move on Lebesgue bounded convergence theorem, we remind definitions. First is Lebesgue measure. The length L of an interval A with the endpoints A and B is defined as the difference of the endpoints, that is L of A is equals to B minus A, that is Lebesgue measure is length of the interval. And the second definition is measurable function, an extended real valued function f defined on a measurable set E is said to be measurable function if for all x belongs to measurable set E such that f of x is greater than alpha is measurable for each real number alpha is any constant. Now, Lebesgue bounded convergence theorem. Firstly, the statement is let f of n be the sequence of measurable function defined on set E. E is measurable set of a finite measure. Suppose there is a real number m such that mod of fnx is less than equals to capital M, that is fnx is bounded function for all x and for all n. Now if fx is equals to limit n tends to infinity fnx for each x belongs to E, then we have to prove that f is Lebesgue integral on E. And second is integration of f over E is equals to limit n tends to infinity integration of fn over E. Now we prove the theorem. Let f be the limit of measurable function. If f be the limit, we know that limit of a measurable function is also measurable. So f is the limit so that f is also measurable. And we also know that f is bounded function. So being a bounded and measurable for an E, it is a Lebesgue integral. Now we prove the second part. Now we know the result that let E be a measurable set with the measure of E is less than infinity, and fn be any sequence of measurable functions defined on E. Let f be a measurable function such that fn x converges to f of x for each x belongs to E. Then given epsilon greater than 0 and delta greater than 0, there exists a measurable set A such that A is contained in E with measure of A is less than delta, and an integer n such that mod of fnx minus f of x is less than epsilon for all n greater than capital N and x belongs to E minus A. Now we use this result. We have given that epsilon is greater than 0. So by the above result, there exists a measurable set A such that A is contained in E with the measure of A is less than epsilon by 4m and a positive integer n greater than 1 such that mod of fnx minus fx is less than epsilon by 2 measure of E for all n greater than equals to capital N and x belongs to E minus A. Also we know that fnx is bounded, so mod of fnx is less than equals to capital M for all n belongs to capital N and x belongs to measurable set E. Therefore mod of fnx minus fx is less than equals to 2m. Here we use the result that mod of fnx minus fx is always less than equals to mod of fnx plus fx, and we know mod of fnx is less than equals to m and mod of fx is also less than equals to m. Fnx and fx are both bounded functions. Therefore we clearly say that mod of fnx minus fx is less than equals to 2m for all x belongs to the measurable set E. Now we take mod of integration of fn over E minus integration of f over E into dx is equals to mod of integration over e fn minus f mod of dx, which is always less than equals to integration over e mod of fn minus f dx. Now we also know that e minus a with union of a is always equals to e. It can clearly show by the Venn diagram. So which is less than equals to integration over e minus a union of a of mod of fn minus f dx, which is always less than integration over e minus a mod of fn minus fx dx plus integration over a fn minus f dx, where x belongs to e minus a, and we also know that e minus a and a are disjoint functions, which is less than integration over e minus a fn minus f plus integration over a fn minus f, which is less than equals to integration over e minus a mod of fnx minus fx plus integration over a mod of fnx minus f of x. And we also know that with mod of integration over e minus a fn x minus fx is less than equals to epsilon by 2 measure of e into measure of e minus a, and integration over a mod of fn x minus fx is less than equals to 2m into measure of a. So we also know that e minus a is contained in e, that is e minus a is a subset of e. So by the definition of measure of e minus a is less than equals to measure of e, which is equals to epsilon by 2 measure of e into measure of e plus 2m into epsilon by 4m, and which is less than equals to epsilon by 2 plus epsilon by 2, which is equals to epsilon. Hence we prove that mod of integration over e fn minus integration over e f dx is less than epsilon for all n greater than equals to capital N. That is, we can clearly say that integration over e f is equals to limit n tends to infinity integration over e fn x. Hence we prove the theorem. Now the remark is bounded convergence theorem need not be true in Riemann integral. We prove it by an example. So we take an example. Let Ri be the sequence of all rational numbers in interval closed interval 0 to 1. Now we define Sn is equals to Ri, where I running from 1 to up to so on n, where n belongs to natural number n, and for each n belongs to capital N, we consider a function fn such that whose domain is the closed interval 0 1 and whose codomain is R. That is, fn, which is function fn defined as 0 1 to capital R as fnx is equals to 1 if x belongs to Sn and Sn is equals to set of r1 r2 up to rn, and 0 if x does not belongs to Sn. Clearly we can say that fn is bounded, and also fn is discontinuous at n points in closed interval 0 to 1, and namely these points of Sn, that is r1 r2 r3 up to so on rn. Now we particularly take at x is equals to r1. Now left hand limit of fn x does not equals to fn r1, which is also not equals to right hand limit of fn x. Hence is a Riemann integrable, because we know that a function is Riemann integrable if it is continuous, except at a finite number of discontinuity. So by this definition we clearly say that it is Riemann integrable in the interval closed interval 0 to 1. Now we proved that limit n tends to infinity Riemann integration 0 to 1 fn x dx as not in equals to Riemann integration 0 to 1 limit n tends to infinity fn x dx. Now we take Riemann integrable limit 0 to 1 fn x dx is equals to integration 0 to 1 fn x dx is equals to Sn union Sn complement fn x dx. We know that Sn is sum of natural numbers and union Sn complement. Sn and Sn complement are disjoint set and Sn union Sn complement is equals to whole interval closed interval 0 1. So which is also equals to integration over Sn fn x dx plus integration over Sn complement fn x dx. And we know that Sn is a function of value of a function over Sn is 1 and value of a function over Sn complement is 0. So which we have 1 into measure of Sn, and Sn is a sequence of rational numbers. And we also know that if sequence Sn is sequence of rational numbers, so measure of rational numbers is always a 0. So we find that Riemann integrable over 0 to 1 fn x dx is equals to 0. Therefore, limit n tends to infinity Riemann integrable 0 to 1 fn x dx is equals to 0. Clearly, fn is convergent to f, which f when f is defined as fx is equals to 1 if x is rational in closed interval 0 to 1, and fx is equals to 0 if x is irrational in 0 to closed interval 0 to 1. And we also prove that f is not an Riemann integrable on closed interval 0 to 1. Therefore Riemann integrable 0 to 1 fx dx does not exist. Hence, we clearly say that limit n tends to infinity integration over fn x dx does not equals to Riemann integrable 0 to 1 limit n tends to infinity fn x dx. That is, bounded convergence theorem does not hold in the Riemann integrable. Now we prove slightly improved form of bounded convergence theorem. And the statement is, if fn is a sequence of measurable functions defined on set of finite measure, and also we have fn x is bounded, that is mod of fn x is less than equals to m for all x belongs to capital E, and capital E is measurable set, and if fn converges to f almost everywhere in E, then we prove that f is integrable, and integration over E of f is equals to limit n tends to infinity integration of fn over E. The only difference between the bounded convergence theorem and slightly improved form of bounded convergence is that we have in this theorem we have fn converges to f almost everywhere in E. Now we prove the result, since fn is a sequence of measurable functions which is converges to f almost everywhere, so f is also measurable. This proved by the definition of measure. And limit n tends to infinity fn x is equals to fx almost everywhere in E, which is given. Now we from here we can clearly say that integration over E f of x is equals to integration over E limit n tends to infinity fn x dx. We can say it by the proof we have, if f is equals to g almost everywhere in E, then we clearly say that integration over EF is equals to integration over G, and here is the result. Limit n tends to infinity, fn x is equals to fx almost everywhere in E. So we clearly say that integration over E fx is equals to integration over E limit n tends to infinity fn x dx, and which is equals to limit n tends to infinity integration over E fn x. We can here we use the bounded convergence theorem, and here are the references. Thank you so much.